So today, I'm going to kind of look at things on a different perspective than we normally do. Right? Most people are probably familiar with the light switch. Right? Here's the one above the stairs in my house. Turn the light on or off. That way I can see and don't trip going up and down the stairs in the middle of the night. And it's behind the drywall. We don't usually think about the wires, but we know they're there, right? Behind the drywall here, there's a wire running up, and since we're leading into computer stuff right now, that wire has a 0 on it. Right? The switch is open, which means it's turned off. The switch is open, so electricity can't move from the source, wherever that's coming from. I'd have to take the drywall off to see whether it's up here or down here, but I'm gonna just, for simplicity's sake, let's say it's coming in from the bottom, going out the top, because the light's on the ceiling. That makes it easier to point. So, coming from the breaker box in here, we have a 1 coming up, but our switch is open, so the signal can't get past it. When we close our switch, well, now we have a 1 on the wire up here, which feeds into the light bulb and turns that on. And we don't usually think about that, but a computer is really just lots and lots and lots and lots of switches. So let's talk about some of the switches, and in subsequent things we'll see how they build up together and do stuff. But first off, let's just look at the switches. So the ones we're familiar with, where we flip by hand. And, we could flip a switch pretty quick, but not as quick as a computer can. So when a computer flips its own switches, it can do it a whole lot quicker. So let's talk about the switches that a computer's going to flip on its own. Okay, so switches. So it's been mentioned a couple times in these videos so far. Computers are just lots and lots and lots of switches. We saw the logic gates, how switches go together to control the output. We can put switches in certain orders to control an output. It's really slow when we flip them by hand, so we want the machine flipping its own switches. Might as well start with the historical ones. I'll create history here. So in the early days of computing, we used what was called bimetallic strips and mercury switches. We'd take 2 pieces of metal, for example, maybe copper and nickel, and weld them together. Just little strips of metal. And then there are different types of metal. And when metal's heated, it expands. When it's cooled, it contracts. You may be familiar with that. And it's not equal for the type of metal. So if we have, like, say, nickel and copper together, when we heat it up and cool it down, those 2 metals are going to expand and contract differently, which causes it to curve. Curve up when it's, when it's cool, and curve down when it's hot. Depending on the temperature, there's some more precise values that go in there. You may have seen these old thermostats used them. I simplified the picture here. We typically do a coil of them, and that way it would only move just a little bit. That coil is going to kind of go back and forth. And at the end of that, there'd be a little glass tube. And that glass tube would be our switch, our actual what controlled the switch. So coming out of our glass tube, we have wires to tie into a circuit. And they kind of run into the tube a little, but not connected to each other. They're separate from each other. And inside of that glass tube, there would be a little bit of mercury. We'd have a little bit of mercury, a liquid metal, sitting inside of that glass tube. So that when, like I drew the picture here, when it's cooled down, that bimetallic strip curves up, the liquid runs to the bottom, and those lines aren't connected anymore. But if we heat it up, that liquid's going to run to the bottom here, curve down, the liquid runs to the bottom, and it's a liquid metal, so it forms a connection there and closes the switch. So turning it on and off based off the temperature. And we can heat things up really easily. have little heating coils on every switch, similar to an electric stove, a space heater, toaster. Oh, coffee maker is probably closest to your coffee maker because we don't have to heat it up very much to get that effect. But a small, like the heater in a coffee maker, we just turn it on, heat it up really quick, and then we turn the switch on, and then we turn it off, and a big radiator would cool it off. Or would cool it down, which turns it off. And that's how the early switches work. Obviously, heating coils take a lot of power. If we have hundreds of them right next to each other, there's kind of a fire risk, right? You might be familiar with that from like space heaters and toasters. With just one heating coil, there's kind of a fire risk. So if we have hundreds of heating coils, there's a big fire risk. The radiators had to be huge because heating stuff up is easy, but cooling it off takes a whole lot more. So there was a lot of drawbacks, but the machine was able to turn on and off those heating coils, thus turning on and off the switches. But there was a demand for something better. And that's where transistors come in. That's what most of this video is going to be about, is transistors, because that's from, we'll mention some other ones, but yeah, mostly transistors here. So there was a demand for a better type of switch, and that would be a transistor. So the one you're probably more interested in here, those Dangers created a need for a better switch. Dangers, and it's still pretty slow, because we have to wait for the heating coil to heat up, the thing to flip, and then wait for it to cool back down. So it's still kind of slow. We can do it rapidly, but it's also dangerous. So that leads into creating a demand for a better one. Transistors, and spend a little more time here because this is the one probably interested in. This is the one we use in computers. Some variant of transistor. So first off, a little chemistry about how this works. So silicon, that's the one you're probably familiar with. It's a semiconductor, which I'm going to draw what's called the Bohr model of the atom. You may have seen this one before. It's where we have that nice little nucleus of protons in the center, and then some electrons orbiting around it. Nice and organized. It's not accurate, but it's generally considered more helpful for humans for visualizing what's going on. And they come in different rings. So in the innermost ring, there's going to be 2 electrons. And then the next one out is going to have 8 electrons in it. And then the next ring out it's also going to fill up when there's 8 electrons there. But silicon only has 4 electrons in its outermost one. So it is exactly half full, which exactly half means the silicon atom is just as happy to give away those electrons as it would be to pick up 4 more. It just wants that needs to be full. And giving away those 4 would leave the next ring down full. So the outermost ring would be full. Or getting 4 from somewhere else would leave this outermost ring full. It just needs to be full. So if it gives them away, then there's more protons than electrons, so it has a positive charge. And if it gets 4 more from somewhere else, then there's more electrons than protons, so it has a negative charge. Thus, it can act either as an insulator or a conductor. So that's what we call it, the semiconductor. It's exactly halfway between. It's just as happy to be either way. And, well, it only needs 4. So a good place to get 4 more would be more silicon. Right? So we set up a bunch of little silicon atoms, and I'll just draw 2 of the picture. And 3, 4. Then a couple silicon atoms share their outermost electrons, and they're just sharing them, so it's going back and forth, but both of them feel like they're full. A nice stable state. So a bunch of pure silicon, it's all going to form a nice little grid. Everything's got a full outer ring of electrons. Everything's happy. And then we can go in and mess that up. Typically, we'll use a process. We go in and do what's called doping. We go in and mess it up. We either add a phosphorus, atom in, or we add a boron atom in. So, if we add a phosphorus atom in, I'm going to skip to the end of the chemistry section. It's not a chemistry class. If we add a phosphorus atom into this, there's an extra electron. Because phosphorus will bring in more electrons than are needed. So, for most of the rest of this time, I'm going to refer to that as a plug. That extra electron is like a plug. And if we dope it with boron atoms, then we're missing an electron. So, going back to this model, boron only needs one. So it's a lot quicker to grab one than silicon can go do anything with four. So if we dope it with boron, it's missing an electron, and for the rest of this video, I'm going to refer to that as hole. So the electron is either a plug or a plug if we doped it with phosphorus, so there's an extra electron, or if we dope it with boron, it's missing an electron from being nice and stable. We call that a hole. And our technical terms for this, if we dope it with phosphorus, that's called N-type silicon. And if we dope it with boron, it's called P-type. So we can mess up this nice little balance and prevent pure silicon from stabilizing on its own by adding phosphorus or boron to create either N-type or P-type silicon. And I'm going to refer to those extra missing electrons as plugs and holes for the rest of this video. So I'm going to go ahead and pause the video, render this down while I erase the board, because there's no need to watch me erase the board and get ready for the next picture. I'll be back in just a second to actually talk about transistors and how N-type and P-type silicon can be used to form a switch. Then once we have those types of silicon with those distinctive properties, obviously the ones with extra electrons, the N-type silicon, we're going to have extra electrons, so that's our plugs. And our P-type silicon, we can basically make a sandwich out of it. So then our P-type silicon has all the holes, and we sandwich that between two N-type silicons with those plugs. And that's the parts of a transistor, in particular an NPN transistor. We can also make a PNP transistor. I'm going to use an NPN for the pictures, but this stuff should translate right over to an NPN. It's just our charge exchange. So if we have an extra electron, that means we have a negative charge. If we're missing an electron, all our atoms are going to have a slight positive charge. And again, a negative charge over here. So here's our wires going out to our circuit. So the quick, easy way to put this, and a good one to visualize, that often shows up in electrical engineering textbooks, is at this point, we just say the plugs can't get past the holes. Right? The plugs, it's a circuit, so electricity trying to flow, our plugs are going to go across here and get stuck in the holes and can't make it across. So the switch is off. What we could do is bring in a third pin, bring in a bunch of extra electrons flowing on it. Electrons flowing, that's current, but that's electricity. Those extra electrons are going to fill in all the holes, and then our plugs can't move across. It's a quick, easy analogy. And a good way to think about it, to visualize it, right? To quickly visualize, try to wrap your head around something real, just think about how plugs can't move past the holes. Or vice versa, if we have a PNP transistor instead, the analogy kind of breaks down because our holes can't move past our plugs. Maybe you can think of it as like a ring toss game, or really an anti-ring toss game, where you're tossing a ring, but there's so many pegs that when you toss the ring, it can't make it past all. The goal is to make it past all the pegs. But there's so many pegs, the ring's going to get caught on one of the pegs. Maybe the analogy works that way. But you can think of it that way. These extra electrons can't flow past the holes because they're going to get stuck in the holes. The plugs can't get past the holes. So we're bringing the side current, filling all the holes, and then the electrons can flow. But there's something, well, we go ahead and go over the actual version. I'll try some colors. So let's say the positive, so we have a positive charge there, and I think I have some more color. There's a green one. If those colors are showing up, I'll make them red and green. Hopefully it'll indicate a little bit better. And maybe at some point you've seen magnets, heard about magnets or something, so you know the positive and negative things attract each other. So right here, this border between them, well, there's a positive charge here. So that positive charge is going to kind of attract those negative electrons, and vice versa. Kind of goes both ways. But we end up with it organizes itself. So that right there at that edge, as the things balance out, the positive attracts the negative, or vice versa, we're going to end up with more electrons right over here at this edge. Because some of these ones are here, these extra electrons, we're able to get right over to the edge, which gives us a negative charge right at this edge. And same thing, they came from over here, so we have a slight positive charge right there. And then we'll have the same thing over here. Those electrons that were attracted to that positive polarity of the p-type silicon left a slight positive charge there, and a negative charge there. And just some quick electrical theory. We always hear about electricity trying to get back to ground. And it does it because that's a stable state. That's a good organized state. Everything's in order. When the electricity flows back to ground, there is a definite positive and a definite negative. It's nice and organized. Well, here at our junction, we created that. It's stable there. And that's why it's not flowing. So electricity can't flow because it found a stable state. Right? Let's give electricity a personality. It's flowing down its line, and it suddenly hits a nice stable spot. Right? It's this nice stable spot. There's a clear organization between positive and negative polarity, and the electricity is like, oh, this is comfy. I'm just going to stay here. That's kind of what's going on. It's stabilized. And once it's stabilized, it's going to stop flowing because electricity already found a stable state. And then we come in and mess up that stable state. So this middle pin, we add electricity to this now, well, that's going to bring in a whole bunch of extra electrons. Then we have a bunch more positive charges here. So you can see the negative and green electrons, there's a bunch of them here. That's going to come over here and mess up this whole nice stable state. And at that point, electricity is flowing again. So that's when it comes up. And a PNP works exactly the same, except the polarity would be reversed. So that we mess it up by we normally keep a charge there, and we mess it up by removing the charge on a PNP. So an NPN transistor, when we apply a voltage, or send in a current, we mess up that stable state. And in a PNP, when we remove a voltage on that middle pin, we mess up the state in electricity. We mess up the stability, and the electricity can flow again. So that's kind of how it works. And some terms for this: our two outside pins are called emitter and collector, and our middle term is called a base. So electricity, we wire it up, so we want electricity to flow between the collector and the emitter. But it stabilizes right at that junction between the N and the P silicon. So we apply a current to the base to mess up that stability, and then the electricity can flow again. Right? Electricity's coming down the line, goes through here. It's that nice country spot, right? Like a long walk. Take a long walk and you suddenly see a nice park bench. Trying to walk your way across the city, see a nice park bench. Like, oh, there's a good spot to rest. You sit down. It's like, oh, this is comfy. I'm gonna sit here and rest. And then it's all comfy. But then suddenly all kinds of chaos happens, right? The local bus stops and lets 30 people off, right? Maybe rush hour. It's huge. A bus full of people get off, and then suddenly it's crowded around your bitch. It's like, oh, okay, well, maybe it's not so comfy of a spot, so then moving on down the line. Kind of like that. It stabilizes itself so it no longer flows. Because that's the electricity flows to ground, or whichever way we draw it. The labels were there before we knew what actually happened, so we talk about it both ways. I use conventional notation, so I'm always saying, in all these videos, I will refer to the electricity flowing from positive to negative. So electricity is trying to do that in order to stabilize. And inside a transistor, it already stabilized. So we mess up that stabilization and turned it on. That's kind of how a transistor works. Let's take a look at a circuit with one of these working. And here is the code for the Arduino controlling today's examples. Same code for both of them. When I first plugged up the circuit, I just picked a random digital pin and then just used that number. It didn't need to be anything complicated, just one of the pins, set it as an output, and write that high, wait half of a second, so 555 milliseconds. It's easier to push 555 than 500. So wait half a second, then write a low, wait half a second, and then repeat. So turn the output of this pin on, wait half a second, turn the output of this pin low. And just to make note of it, keep mentioning on, off, high, low, true, false, different things. The way high and low are written in the Arduino IDE here with the capital letters, and then it turns blue because it recognizes it, that really does mean 1 for high and 0 for low. So this is exactly the same as typing a 1 here and a 0 here. It's just the code makes a little more sense when we see the words instead of the 1 and 0. Easier to make sense of, but using this same code for both example circuits today. So just thought I'd show that once. Okay, and here are transistors. So a point I wanted to make is there's a whole bunch of kinds in this little box, and they all look exactly the same. There's some writing on them that is not going to show up on the camera. I grabbed a 2N2222. So both examples today have a 2N2222. We'll talk about it in the second example when we get to that. But for the first one, we're using it as a switch. This is a popular NPN transistor. My go-to is usually a 2N3904 for an NPN. But you can see they all look exactly the same. So this is definitely some components you want to take care into keeping them organized. So I have a 2N2222. So we have a collector over here, over on this side, the emitter on this side, and in between them is the base. So that, like that picture on the board, the power wants to flow between the collector and emitter, but we have to apply some current to the base in order before it will. So a very common component. There's another use other than switches. Another very common use other than switches we'll see in the second example. And I'm using the exact same transistor for both examples. So I'll put this one back in here. And the circuit for today. So here's our circuit for today. Using an Arduino Uno. A disposable Chinese knockoff of an Arduino. So an Uno board. And it's supplying 5 volts and ground to the breadboard. So we have 5 volts running down the rail here and ground running down the rail up here. And then one of the digital output pins is just toggling on and off basically every half second. We just looked at the code for that. This pin's going on and off, and when it goes on, so if we follow that wire through, there's a little purple wire here. You see it comes over and then runs through a resistor. That's just to get the current, the appropriate amount of current to the middle pin on the transistor. It's probably kind of hard to see there, but that resistor is feeding the Arduino pin into the base of the transistor. So that's what's going to turn it on and off. So basically the microcontroller is flipping the switch. And then the power is coming from this white line over to the emitter side of the transistor. And then the collector of the transistor is coming down this wire and powering an LED. So basically Arduino would be enough to, we could just power the LED right from the switch, but we'll get the same effect this way. Instead of going straight from the Arduino to the LED, our Arduino is just turning a switch on and off to kind of express the point from today about switches. So when I bring power to the circuit here, you can see that it just turns it on and off. So whenever the Arduino writes that pin high, writes a 1 to the pin, turns this signal on, it flows through the transistor, turns it on, and when it goes on, the power is able to flow from the voltage source through the transistor, through the LED, and back to ground. And when the signal from the Arduino turns off, the power can no longer flow through there. So just flipping the switch, but you can see it's still just turning the light on and off. It's basically doing the same thing I was doing in the other video by manually flipping it, especially with it slowed down like this, but using a transistor as a switch. And the main point of this video today was to talk about the switches. So there's another one we want to talk about. Let's go over to the board and talk about another one very closely related to this transistor we just looked at. And so a couple of technical terms that we kind of need to move into the next step, which we can talk about quickly. So here, it happens because of these two junctions between the N-type and P-type silicon. And that works whether we have an NPN or a PNP transistor. Between the two junctions, so one thing we could do is call it a bipolar junction transistor, or BJT. And the important part that I will, for this, just a quick introduction, so there's definitely a lot more to get into about transistors. But the important part of why I'm bringing up the terms for a bipolar junction transistor, that is controlled with current. That's our current is doing that. So it's when we apply a current. Current is flow of electricity flow of electricity is electrons moving. So when our electrons are moving, that's bipolar junction transistor. We could also do it with voltages. So when there's a potential for the electricity to flow, and when we do it with the in terms of voltages, that's what's known as a field effect transistor. A field effect transistor, or effect. So BJT or effect. We're usually talking about BJTs and circuit boards. There's another use for them we'll see later in the examples too. But just talking about those switches, the other use, I had to use it, so I'll point at it when we get there, but we're talking about switches today. So bipolar junction transistor, where we control it with the current at the base. And a field effect transistor, we control it with the voltage at the base. And I bring that up because of the next part, so I'm going to erase the board, get ready for the next part, and then be right back for the next scene of the video. The next one that we're going to talk about, because it applies a lot in computers, you've probably heard the term, or there's variants of them, we're just going to talk about one of them for the introduction here, is going to be a Mosfet. And that is a metal oxide semiconductor field effect transistor. I'll write those words over here. Metal oxide, and while I'm putting labels here, I might as well go ahead and write SiO2. In particular, silicone dioxide. Then field effect transistor. So the metal part here, we have connections to our wire. We have the metal there. More metal there. And then the wire coming out. So it's metal for our connections, the wires going through, right? Basically 3 pieces. The in and out, and then across the. Then we have right next to that metal, we put a layer of oxide. We'll stick a layer of, that needs to be up here. We embed those into a layer of silicone dioxide. I guess these need to come under. You could draw in my picture a little bit further. So the metal, then silicone dioxide, and then down here, the field effect transistor layer. I'm going to draw this with P-type out here. So mostly P-type silicone, but we wrap our little things in N-type silicon. Which I don't have much room to overgrate. So you can see we have the NPN transistor going on again. And that's kind of what a Mosfet is. It essentially works the same, have some different labels. Instead of collector, base, and emitter, we have source, gate, and drain. But they're essentially doing the same thing. So, a whole lot like the transistor we just looked at, except we add in this layer of silicon dioxide, which is an insulator, and then we do this with voltages rather than current. Notice that in the base, or the base of our NPN bipolar junction transistor made contact with the P-type silicon. And that's why it's bipolar junction. The current controls it because the electrons actually flow into the p-type silicon. Whereas here, the gate does not make contact with the p-type silicon, so all we have is so we're controlling it with the voltage. Hence, field effect transistor rather than BJT. That's kind of the idea of that. Conceptually, it's just like that was what we just did for the with the diagram for the BJT transistor, and that covers a lot of how the switching in computers works. You know, that can be really, really small. We don't need a very big piece of metal for electricity to flow through, and we do not need a very big piece of silicon for that to get those effects. So that's why we can plug millions of switches in such small areas as like a CPU. Using transistors and Mosfets. And one more switch I want to talk about because these are great, obviously, for computers. Small things, right? Low voltages. But those aren't our only machines that need this, right? We might need that on big machines. So the transistor, like the one I used in the example earlier, it can handle up to 6 volts between emitter and base and emitter. And I think it maxes, I'd have to check data sheet. I'm pretty sure it maxes out around 60 volts. So 60 volts is a little bit, but that's not going to run much in your house, right? Not going to run your coffee maker. Definitely not going to run your stove. You might get some small stuff, but most of the stuff in your house that wouldn't be enough for. So we need a switch that can handle bigger things, or a more extreme example, like a conveyor belt at a factory. Let's take that to the extreme. The conveyor belt at a factory that makes those giant dump trucks for mountaintop removal mining, those huge, massive things, right? It's going to take a lot of voltage to get that conveyor belt moving. Under those levels of voltages, MOSFETs and transistors would just disintegrate. They'd burn up so quick we would call it disintegrating under those voltages. So we still need our gates and controllers and everything, but these type of switches aren't going to handle that. So we need something a little bit bigger. Or for a lot of people working with stuff these days, for IoT stuff, right? I mentioned running the things in your house. That little transistor I hooked up isn't going to cut it for the coffee maker. Right? If you want to hook up a Bluetooth chip so that on your way home you can grab your phone now from a stoplight. Don't do phone stuff while driving. You're at a stoplight. If you stoplights from your house, you can put your phone out and hit a switch because the coffee maker's got a Bluetooth chip connecting to a network, or a Wi-Fi chip connecting to the network, and it turns on based off these same types of controllers that we use in computers. But it needs a little more voltage than that. So let's look at a switch that can handle larger voltages and kind of works about the same way. So we need about the same thing. We need the machine to flip its own switches, but we have some extra requirements too. In the case of IoT stuff, that's kind of why I'm including this, because it's important for networking things that aren't computers in our houses to the things that are computers to control them. For example, a kitchen, starting to put together a smart kitchen and control everything from a Raspberry Pi. You have 3.3 volts to control everything. But 3.3 volts isn't going to be enough to turn your stove. You got running some errands, running late, and need to go ahead and start dinner while you're still walking around Walmart or something, and you want to do it from your phone. You can get a signal to the Raspberry Pi, and then maybe it's up in the shelf, safe from water, and then everything in your kitchen has Bluetooth chips in it so that it just picks up the signal from the Pi or something. And gets controlled with the 3.3 volts. But that's not going to turn on the oven. That's not going to power the oven. We need more power. And the power to turn on the oven would definitely destroy the Raspberry Pi. So we need to isolate these things. We need 2 separate circuits, completely isolated from each other, so that one doesn't affect the other. And we do that with a piece called relays. And unlike the other ones we talked about, so all the ones we've talked about so far, those are electrical switches, right? Even those historical ones, we used just electricity to create a heating coil. But definitely MOSFETs and transistors, it's all electrical stuff. But to isolate things, we're going to need to get into electromechanical things. We need a small current to do something mechanical to activate a larger circuit. And the way it sets up is something like this. So we'll have a small coil of wire. We could do it off just a regular wire, but it's better if we have a coil because then we have more wire. Is the idea there? But we'll run our small current through that, such as the 3.3 volts from a Raspberry Pi. And then one thing about electricity is electricity and magnetism are very intimately connected. So if we go to plot out a wave of one or the other, we have to kind of have plot both. So maybe our electricity goes this way, just like that. Then our magnetism would be kind of coming in and out of the board. Starts to look like a mess unless you got a bunch of nice colors or do it in 3D graphing software, but our electricity is going up and down, and as it does it, there's a current going in and out perpendicular to it. So anytime electricity passes through a wire, we get a magnetic field. We can take advantage of that magnetic field and operate mechanical things. So we'll have a little lever here, some sort of fulcrum in the middle, and then this connects to a big wire, some big voltage there. Then over here, I'll put a little stand. We have the other end of that big wire, the big current that we want to flow through. And so to open this, keep the circuit open is kind of easy. We can put a small spring here so that if everything's just sitting there on its own, this small spring pulls the bottom of the lever, which pulls the top of the lever, thus opening the circuit. And then we can take advantage of that property I just mentioned so that when a current is flowing through our wire, when our electricity starts flowing, it's going to produce a magnetic field around this coil of wire we have here. And magnets attract metal, so when there's a magnetic field here, our little lever is going to spin, right? When the current flows, there's a magnetic field which will pull harder than the spring and flip our lever to close the switch and complete this circuit so that the high voltage flows. And then when we're done, we just turn off the little current, the magnetic field goes away because there's no longer a current flowing, and that little spring can pull the switch back open. It's kind of the idea of how it works. And this is the one I wanted to include because that's going to be very important for IoT stuff, right? Raspberry Pi is running 3.3 volts. ESP8266, that's a Wi-Fi chip, which has been expanded into its own microcontroller. So now instead of hooking the Wi-Fi chip up to a microcontroller, the Wi-Fi chip is a microcontroller now, which is pretty sweet for making IoT stuff. But the small voltage, 3.3 volts, or up to 5 volts, not enough to turn on a coffee maker. Most of the stuff in the house is going to be 110 volts, right? Whereas all our microcontrollers are going to be less than 5 volts. So with 5 volts, we can do this, create a little magnet that turns on a switch. So we have to get into electromechanical stuff, and when we do it, it isolates stuff. This 110 volts will not affect the 5 volts, and the 5 volts will not affect the 110 volts. They're isolated from each other. So let's go take a look at that in action. Okay, and so here's what a relay looks like. If I bring it in here, if autofocus will cooperate a little, there we go. So you can see this top row of numbers, 250 volt AC, 125 volt AC, those are easily the range for things in the house. And 10 amps, that's plenty of amps for most of the stuff in your house. So these are good little ones for IoT stuff. And let's see this corner. So on the bottom we have 5 pins. So these two, those are our coils. So we'll bring a small current in there, such as from a microcontroller. And when we apply a current, as it flows between those two, on the inside here, it runs through a coil like out on the board and creates a magnetic field. This one over here will send outputs to these two. So we bring our electricity in over here, and then it's going to come out these two. And the difference is that this one is normally open. So normal means when the power's off. So if there's no current flowing through our coil, so our small current is off, then this pin is off. And this one over here is normally closed. So it's normally on, which means when there's no current, this pin is on. So we have a choice of how to hook things up. We hook up this one, and then it comes on when we send a current through our coil. Or we can hook up this one, and it goes off when we send a current through our coil. Different situations call for different connections, but that's what a relay is. So the circuit for today, I just basically replaced what was in that first circuit with transistors with a relay. Move that out of the way. A couple things of note here. When we shut off the current through our coil, we get what's called back EMF, right? What's a short way to put it? Well, like I put in the picture on the board, a current creates a magnetic field, and that goes the other way too. A magnetic field creates a current. A changing magnetic field creates a current. So when we turn that current off, our magnetic field dissipates, which is a changing magnetic field. So that's going to create a current going in the other direction. And when we use microcontrollers, we want DC current, so we want our current to always flow in the same direction. So we have a diode, which that's just N-type and P-type silicon put together. Sorry, N-type and P-type silicon sandwiched together, just one of each. And then that is kind of like a one-way valve for the current electricity. It can only flow one way through a diode. And then something else I had to do here, I wanted a little bit more amperage from an Arduino to power this relay, because the relay power is a big thing. So I didn't want to use just a voltage coming out which had almost no current in it. So another use for transistors, besides switches, you might notice a transistor here, is we can also use transistors as amplifiers. So I have a transistor here working as an amplifier rather than a switch, just to get more current flowing through that coil and produce a better magnetic field to operate that little lever quicker. A second use for transistors, but we're talking about switches here. So a relay for a switch. Oh, and this one, compared to the other one, on one of my relays, I just soldered on some long leads that are plenty long enough to bend easily and seem to work with a breadboard a lot nicer for testing things. So we can send a big current through it, but in this case, I'm just sending 5 volts through like the earlier example. Same code running it. This pin goes high, waits for about half a second, then goes low, waits for half a second, and keeps toggling. So when I bring power to the circuit, you can see it's kind of doing the same thing. As when I use the normally open circuit, so that when current flows, when the Arduino supplies power to the coil, the light comes on. And then when the Arduino is not supplying power, the light goes off. And notice with the relay, you can hear it. That's that That's the mechanical part, right? We have actual little metal pieces moving in there. So we can hear it clicking as it moves back and forth. An electromechanical switch. So that's what a relay looks like. And then another use for transistors is, if we can kind of find a good spot, that transistor there is being used as an amplifier rather than a switch. Another use for another thing we can do with transistors. So let's go back over to the board and kind of wrap everything up here. Okay, and that's kind of a quick introduction to switches. Computers are just lots and lots and lots of switches. And it's hard to see it because they're flipping so quickly, and we're doing stuff with those ons and offs. And when we program a computer, that's what we're doing. We're just feeding in instructions for which of its switches need to be on and which ones need to be off. Traditionally, we've done that in text files with an encoding scheme based off our own language, letters and numbers and symbols that we've assigned meaning to. And the computer translates that into a bunch of on and off instructions. When we run a loop, that's what, we're telling the computer, keep doing all of this stuff until these switches go off, or something like that. When a computer makes a comparison, that it subtracts them. 1 0 0 1 0 0 0 1 0 0. It's just going to subtract those two numbers. 0 minus 0 is 0, 1 minus 0 is 0, 0 minus 1 we have to borrow. So 2 minus 1 is 1. Oh, we had to borrow from that. So 1 minus 0 is 1. We already took that one away. So it subtracts them. We ended up with a positive number, which means, so this minus this, it was a positive number, which means this one's bigger. If we subtract them and get a negative number, then that means this one was bigger. So it can compare them. Obviously, if we get all zeros, then they were equal. So the computer, when we program a computer, we're just giving instructions on how to flip the switches. And who knows, maybe that could be useful if you're stuck on a big problem sometime. Think back to switches, give you a different perspective on it. Usually we don't, because it's kind of hard to think at that level, especially if we're doing very much. But that's what a computer is. Talk about transistors and relays. Those are the big ones you're going to need if you're doing some IoT stuff. And yeah, it's just kind of a basic one. I figured one of the main things is I figured people were curious about transistors. We hear about them, but you probably didn't know how they worked. And yeah, just lots and lots of switches. Just trying to get some of them. You may have heard that the computers are just lots of switches, and trying to remove some of that mystery about how it does so much stuff with such a simple piece.